Hi everyone. Today we're doing a mechanics, A2 mechanics paper. So let's get started. So we're talking about particle motion, and we've got an elastic string involved. So the formulas we're going to need are found in the formula booklet. We have the good old classic, which you're very familiar with by now, F equals ma. And we also have that the tension in some elastic string is equal to the modulus of elasticity times the amount that it's been stretched, which I'll call delta x, or I think the formula booklet just says x, over the natural length of the string. So here we were given the modulus of elasticity. We're given the mass of the object on the string. And the last equation that we're going to need is that mv squared over r is equal to ma, or, well, more simply, rotational acceleration. Forgive the graphics tablet problems. Gravitational acceleration, let's write it like that. Sorry, rotational acceleration is equal to v squared over r, where v is the tangential velocity. So if you're moving along a circle, then the tangential v velocity is like your instantaneous velocity tangent to the circle in which you're moving. So here all we have to recognize, so we have our setup, say our center O, some string, and we're told the natural length is L, and that it's been, the thing is moving in something of a radius 2L. So this is delta x, which is also equal to L. So essentially the movement has doubled the size of the string. It's going around like this. It's got some velocity v. This is p. Now you just have to equate. We recognize that the tension in the string, like this, is the only force acting on the particle. So any acceleration it undergoes must be related to that, using F equals ma. So we have the tension, which is lambda, delta x, which is L, over L, so that's the tension, is equal to the mass times this acceleration, v squared, over r, and r is 2L. So we can then solve for L. These L's cancel. This L goes over there. L is equal to mv squared over 2 lambda. Just plug in the values they've given you, and you should get the answer. Right. Question 2. This is a center of mass question, and it relies on you realizing that if you have some compound object, some rigid body or something that can be considered to be made of separate pieces, even if like this is one piece of wire, you just need to add up the coordinates of the center of mass for each one in a certain way that's given in the formula booklet, and you can calculate. So you can calculate them separately and then use the formula to work out where the center of mass of the entire object is. So let's draw an axis. I'm going to choose to draw my axis very badly like this. That's the y-axis, that's the x-axis. So I know what I'm talking about. Now let's look at the larger circle first. I'm going to talk about the larger circle up here. Well, we know that the y-coordinate of its center of mass is going to be decided by. In fact, we can draw a vector expression. So let's say x as a general vector. So it's got an x component and a y component. Of this arc, And let's call it L for large. So we want this, and we also want x small. Well, the formula booklet tells us that the center of mass of an arc of a circle. So here, what they mean is an arc of a circle, meaning like a wire that is stretched into a circle, not a section of a disk. So that would use the word disk. An arc is just sort of some line that forms the shape of a circle and it's empty inside. So they say that, well, so see an arc of a circle subtended by an angle theta is equal to r sine theta over theta from the center, so the center of the circle. So not the center of the semicircle, but the center of the circle of which it is a segment. So we know that the x-coordinate of the center of mass of this larger circle is going to be 0 because it's symmetrical along that. But we don't know what the y-coordinate is. But we know that here for the large one, theta, well, it's a half circle, so theta is equal to pi. That means the sine of theta is 1 from, there's 1, wait, sorry. Theta is equal to pi sorry, I made a mistake. It's very silly. Okay, hold on. Okay, sorry, I made a mistake with this one. We're actually supposed to be looking at the, let's look at the smaller circle first. Pi over 2. Okay, there's some misinterpretation when I read this from the language of the formula booklet. When they say the circle center, right, okay. I've realized what they actually said was the center of mass subtended by theta is equal to, by 2 theta is r sine theta over theta. Right. So the angle theta, sorry, the angle 2 theta is equal to pi. Therefore, theta, so this is for a semicircle. So we're saying that this angle is 2 theta. And this is true for either of them. So theta is pi over 2. So that was, I was confused. I was getting like sine of theta is equal to 0, which obviously is not going to be true. So back to work. Large one. We have that the distance from this point, so basically the y coordinate, so this distance here, is equal to the radius, 0.6, sine pi over 2, which is indeed 1, all over pi over 2. So this is in radians, by the way. And this is equal to 1.2 over pi. So we know the x-coordinate of that, and the small one, well, that's going to be some distance from this point, right? So it's got a radius of 0.3. And the distance from that point is going to be, so let's say the y coordinate is going to be minus, because it's downwards, 0.3 sine pi over 2 over pi over 2, which is minus 0.6 over pi. So the equation that relates the center of mass of each individual object to the center of mass of the whole object is this one. M total, let's write it in a nice fancy color. M total x total, so this is now a vector and it's true vectorially, is equal to m1 x1 plus m2 x2, and if there's more components, you add them on the end. So in our case, just to be exhaustive, because we will need it in a moment, I'm going to work out both the x and the y components. So the total mass, let's assume that there is a mass density per unit length. You'll see it'll cancel, so we don't need to worry about what it is. Per unit length, lambda. So the total mass is going to be lambda times this length plus this length. Well, this length is just pi r, and this is 0.6 pi, and this is 0.3 pi, so this is 0.9 pi. That's the total mass. Is equal times x total is equal to mass of the first one, which will get the large one, let's say. So it's the large one, and that's the small one. Mass of the large one is 0.6 pi lambda x. So let's actually put it in. The coordinates, the x coordinate, well, it's just 0. And the y coordinate is 1.2 over pi. And for the smaller circle, we have 0.3 pi lambda times, sorry for the cramping, and here the x coordinate is 0.3, and the y coordinate is minus 0.6 over pi. Okay, that's pretty horrendous, but you see, so if I just actually drag all of this. Okay, that's not working for some reason. Okay, I just drag this over here so we can see it a little more clearly. So I can look at both the x and y components of this individually. So let's look at the y components. So first you see that lambda cancels. So we can not even worry about what the density was. And then let's see that this pi and that pi also cancel with that pi. So we get 0.9 x total is equal to 0.6, 1.2 over pi plus 0.3, 0.3 minus 0.6 over pi. And they're asking us, so finally, let's actually get to the point. They're asking us for essentially the y coordinate of the center of mass, because they're looking for the distance from A, C, B. So let's solve for the y section of this. X, well, it's called y total. So the y coordinate of the center of mass of the total object. Y total is equal to this one is 0.6 times 1.2 over 0.9 pi plus or minus 0.3 times 0.6 over 0.9 pi. And this you'll find is, as they say, 0.191 meters. So that's this question done. Now you'll wonder why I spent so long talking about like this general formula, but you'll find we'll need it for this next section. So let's have it down here. Okay, now the object is freely suspended and hangs in equilibrium. So when something is freely suspended and hangs in equilibrium, what that means is that the point at which it's suspended is directly above its center of mass. Else it would start swinging, it wouldn't be in equilibrium, there'd be some net force. So let's think about this object hanging at equilibrium. So it's going to look something like, so this is going to be come on. So, okay, something vaguely like that. And so we're imagining this is the x-axis we had before, and this is the y-axis, and the center of mass is here somewhere. So really, we need to know the angle. Oh, that's what they're being asked. The angle here. So that's a right-angled triangle. Well, if we think of this right-angled triangle, what are its sides? Well, we know that this height here, well, this is just the y-coordinate of the center of mass. And this height here is just going to be, so if we get really detailed in here, this was the x-coordinate of the center of mass. So this whole thing is going to be this radius plus the x-coordinate of the center of mass. So 0.6 plus x center of mass. Well, we have all of those. We have that y center of mass is 0.191 meters. And we can solve this for x. We have x coordinate of the center of mass is equal to, well, that's part is 0. It's equal to 0.9 over 0.9, sorry, 0.09, sorry, 0.3 squared, 0.09 over 0.9, which is 0.1 meters. And now we have that the tan of theta, which is where theta is that one, is y center of mass over x center of mass, and you just use the inverse tan function to get your value of theta. So you see, it was important for us to remember to work out the x value as well. Okay, question 3. This is a sort of simple differential equation question. Now, this is this first part. They've given us the force acting on this object. So let's just draw our setup. It's always good bookkeeping. Flat surface, small block B, force acting. Now we're told that F is equal to 2 plus 0.3 x squared. And we know that F is equal to ma. What is A? A is dv dt, right? Now we want dv dx, so we just apply the chain rule. dv dt is dv dx dx dt. Well, what is dx dt? It's just v. So you equate those two, you divide by the mass, you get this expression here. That's all. Okay, so find the velocity of b when x is equal to 1.5. So they're just asking you to integrate this equation. So we have just a separation of variables question. We keep the v on this side and the dv, and we take the dx over to the x side. And then we integrate. Now, we need limits if we want to get the actual velocity. So let's put our limits to start at the point of release. Its velocity is 0. And at the point that we're interested, its velocity is v, which we were trying to find. In which case, this is just a subtlety, but this v is now symbolizes this actual velocity at some time, at some later time or a later point. Whereas this one is just our dummy v variable within the integral. So we tend to put a prime on this, so we sort of know that this is just something that's integrated over all values of v between 0 and this actual value of v. Now, the limits have to match. So at the same time as the velocity is 0, the displacement is also 0. And the upper limit, where we're trying to find v, we're told is when x is equal to 1.5. So this thing is just going to be 1/2 v squared is equal to 1.2 over 3 x cubed plus 8x, evaluated between 0 and 1.5. And if you work it out, this gives us v is equal to 5.17 meters per second. Now, they're giving us an additional force. So we basically just work backwards for this, but we're given the way in which the force modifies the differential equation. So remember that this thing, well, that was just equal to F over M, because that's how we got it. And that is the net force is the one that's applicable, because the velocity is the net velocity. After this x is equal to 1.5 point, when there is the additional force, this is what happens. So we say F net is equal to, let's say it's equal to the first force that we had before, plus this new force. And that is going to be equal to this thing times the mass, which is 0. So let's give it 0.3x squared minus 3 quarters x minus 1.5, just going backwards, multiplying by the mass. And we know what F1 is, so we should get that F2 is equal to minus 3 quarters x minus 0.5 newtons. Now, what does this minus mean? Well, we implicitly defined our axes, our positive x direction, as along that way. Like this is plus x. So forces, when they were positive, meant they were acting in that direction. Acceleration was positive in that direction. Velocity was positive in that direction, so on. So if it's negative, all that means is acting in the opposite direction. So you'll say something like the magnitude. This is only one direction. We don't have to worry about different components. The magnitude 3 over 4x plus 0. That should be 0.75. 0.75 towards the origin. Okay. Next question. So this is another center of mass question. So again, let's draw our axes. Always good practice, because then you can know exactly where everything is in reference to anything else. So I'm going to draw mine here and pick that as 0. My y-axis, This is my x-axis. Now, again, I'm choosing to split these two, this object into these, a triangle and a square. We know it's a square actually because this is A and that's also A. Actually, it's not a square, my bad, it's a rectangle. But we don't know what A is. So my first square, well, obviously the center of mass is going to be right in the middle. So we've got no problem there. So the coordinates, I'm just using x as a vector of the square. Well, that's equal to, x coordinate is minus a over 2. Y coordinate is 0.45. But the triangle is a little trickier, and it's in your formula booklet. But the idea is that the center of mass of a triangle is always going to be, if we imagine drawing one of these medians from a vertex to the midpoint of some other line, then the center of mass is always 2/3 of the way along from the vertex to the midpoint. So 1/3 along this direction. Well, we want the coordinates at this point. So, so the midpoint, well, that has an x coordinate of 0 and a y coordinate of 0.45. No problem. So how do we get to this point? Well, we can go from O to M, and then 1/3 of the way along the path from M to C. So MC, that's just equal to minus M plus C, which is equal to C coordinate, X coordinate is A, and the Y coordinate is 0.9, so 0.9 minus 0.45, also 0.45. Makes sense. To get from here to here, sorry, here to here, you would go X coordinate along A and up 0.45. So the coordinate of the center of mass of the triangle, let's do it in purple. Just to keep things exciting. That's going to be M, go to M first, plus 1/3 MC. That's 1/3 of the way across that, along that line. So that's equal to 0 plus A over 3 and 0.45 plus 0.45 over 3. And I'm going to write that as 1/3 A 1.8. Taking the third out. Okay, so that's all we need to get the center of mass of the entire object. So let us copy these down here. Well, there we go. And we're going to use the formula that we did before. Remembering that the mass of the square, we're just going to assume that lambda, we're going to set lambda is equal to 1 unit density, or in this case it would actually be mu, I think, because it's a areal density, so mass per unit area. We're just going to say it's 1 because it cancels anyway, like we saw before. So the mass of the square, well, that's just going to be 0.9a, and the mass of the triangle, 1/2 times 0.9a. Fine. And therefore we have the total mass, 0.9 plus 0.45, 1.35a times the x coordinate, the coordinates of the center of mass of the whole object is going to be equal to 0.9a minus a over 2, 0.45, plus 0.45a times 1/3 a 1.8. Now, if you work this all out, you'll get that this x total is equal to minus 2/9 a, 2/9, that's on a, and 0.5. So therefore, we go back to the question. Calculate the distance of the center of mass of the prism from AD. Well, AD is just the x-axis, so the distance of the center of mass is 0.5. Now that seems a lot of work for one question. You didn't have to work out everything in the y-coordinates, but it's always useful. So the answer is going to be 0.545 meters. And then the answer, next one follows straight away. Express the distance of the center of the mass in the prism from AB. This is AB. Well, we've just worked out the x coordinate. So it's going to be minus a plus the x coordinate. Sorry, the x coordinate is going to be a minus the x coordinate. So it's a minus 2 over 9a, which is 7/9 of a. Now, question 3. This is a question about torque. So I'm going to draw our little system again. So so remember this was 0. So our center of mass is around, let's see, minus 2/9 of a, somewhere there, 0.5, blah, blah, blah. Now they're telling us that we've got a force acting like this, and we of course know that we've got mg. And they're saying that the whole thing is about to topple, which means that it's about to turn about this point. You know, this thing's about to go that way. Well, when we have some sort of point about which thing is turning, we have torque from these forces, and the torque will depend on the distance or moment, also called moment, about this point. So the vector equation is that the torque vector is equal to r cross f, where r is the vector pointing from the torque point to the point where the force is acting. And the forces here are all acting in the center of mass, so this is r. And this is one of the f's, and that's another one of the f's, mg. So in this case, we only need to worry about the magnitude of the forces, because they're all acting perpendicular to each other. So this is equal, well, the magnitude of the torque, because we're just talking about one torque going that way, because this one's forcing it to turn that way, whereas this one is asking that it turns the other way. So the magnitude of the torque is now just going to be r, magnitude of f, sine of theta. Well, what is sine of theta? Well, we can imagine this triangle here, and this is so blah 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 blah. This triangle, that's just the x-coordinate of the center of mass, and that's the y-coordinate of the center of mass. And this is r, let's call it. So the torque acting that way, at least the magnitude of it, is F, which they've given us. So like the force that's being applied, which is 6 newtons, times R, times the sine of theta, which here is this angle, So we're talking about this angle refers to the angle between r and the vector f. So in here, in this case, this angle. And the sine of this theta is y over r. So this is equal to f r y over r, which is just equal to f times y, which is equal to 0.5 times 6, 0.5 being the y coordinate, which is 3. Exactly the same procedure for the other one. We get this is equal to mg, oh my goodness, mg r sine, and let me call it alpha because it's the other angle. Well, alpha is this angle, right? And by alternate angle, it's also equal to that angle. So that the sine of alpha is x over r. So this is mgx, which is equal to 4a. And now they're telling us that when this force is applied, the thing is just about to topple. So that means that the torques are balanced. So we have that 4a is equal to 3, or a is equal to 3/4. And that's exactly it. And that's the end. So there was a lot of work up here to get the exact coordinates of the center of mass, but it was worth it in the end because it meant the other questions were very, very easy. We got all the information we needed to know. Okay. So now we have a rotational motion question, but it's also about just resolving things along axes. So let's draw our setup. We have some fixed point on the ceiling and a string coming down with a ball at the end. And it's moving in some sort of circle. And it's hanging at an angle. Let's call that theta. The tension in the string is T, which they've given us, 5 newtons. And we know that the mg is acting on the ball. So we are looking to calculate the speed, and what they mean is the sort of horizontal speed. So we only need to consider horizontal forces. So in this case, there is no horizontal force from the mass. There is only this force, which is T sine theta. Well, first we need to work out theta. That's easy. Within this triangle, we're given, whether the triangle is talking about forces or actual measurements of distance, it's still going to be the same theta. So we're told this is 0.6 and this is 0.45. And that means that the tan of theta is 0.6 over 0.45, no problem. Now, the horizontal forces, well, there's only one, it's T sine theta, so that's our only source of anything that's going to give us acceleration. So, T sine theta is equal to ma, and this is a rotational motion, so this is mv squared over r, kind of like, orbital, but in just that one dimension. So what do we have? We have sine of theta, we have the mass, we have the radius that's moving in, 0.6, and we have the tension of the string, so we can solve for v, no problem. 2.45 meters per second. So that's done. Now, they're looking for the greatest possible tension in the string for the motion. So by this they mean basically the greatest the tension the string is going to get without the thing lifting up off the floor. So when would something lift up off the floor? Well, that would be when this force, T cosine theta, is equal to the weight of the object. So T cosine theta is equal to mg. We know cosine theta, we know the mass, we know g. This gives us T is equal to 6.67 newtons. And then they ask us for the corresponding angular speed. So this is omega. Now, we know that r omega, v, the tangential velocity of an object in rotational motion is equal to the radius times the angular speed, which is often called the angular frequency, but is not really the frequency instead of that being the frequency. So forget about it. So we go back to mv squared over r, which is equal to mr omega squared, just plugging that in. And this again is equal to T sine theta, because the speed in the circle is controlled by the horizontal aspect. And now we know sine theta, we know T, this T, we just found it. We know R, we know M, and that's how we get omega. Right. So this question, again, we come back to elasticity. And here we're just purely going to use conservation of energy. All we have to do is be careful about what we consider the amount of extension, like distortion of the elastic string. So let me see what I mean. At the beginning, T is equal to 0. Well, what potential energy do we have when it's right down there? We have no gravitational potential energy. We're right at the bottom. We have no kinetic energy. We're completely still. What we do have is elastic potential energy, which is, I think it's in the formula booklet, lambda delta x squared over 2L, where this again is the lambda is the modulus of elasticity. This is the amount of distortion, and this is the natural length. So we now need to compare that to some later time. T is equal to T prime. Well, now our gravitational energy is mgh, and we know h because they tell us that for this sub-question, it's on the same horizontal level as O, so h is equal to 0.9. The kinetic energy is 1/2 mv squared, and the elastic potential energy is also equal to, well, the exact same formula, except delta x is now different, delta x prime, all squared over 2L. So delta x here, well, it was the amount that the string is stretched minus its natural length. Well, how much is it stretched? It's stretched half the circumference of a circle of radius 0.9. So 0.9 pi minus the natural length. Here, well, it's only stretched for half of that because it's over here. So that's 0.45 pi minus L. Okay, we have all the energies that are involved. There's no other source. So we set this equal to all of these, and we solve for V, and we get 8.29 meters per second. In the second part, it's the same idea, but you don't know which. Well, actually, you do. We can work it out. It's exactly the same procedure. Let's do it over here. So our kinetic energy at the later time, which is 1/2 mv squared again, is equal to whatever energy the thing had at the beginning. Remember, it was 0 for the kinetic, plus 0 for the gravitational, plus the the elastic energy at the previous time, lambda delta x squared over 2L, minus the potential energy that we have at this point, minus mg h prime. So at this point, h prime is not the same as the one we had before. It's the point at which the string goes slack. Well, that means that it only extends for L. So what does that mean for the length of this arc and its height above the 0 point of the gravitational potential energy? Well, this forms a triangle. We know that the radius is 0.9. Sorry for the noise, guys. And there's some angle alpha here. We know that this arc length is 1.2 meters. So we know that alpha divided by 2 pi, the ratio between the angle subtended by this arc and the full number of radians, remember alpha is in radians, is equal to the ratio of the length of the arc divided by the full circumference of the circle. So that would be 1.2 over 2 pi times 0.9. So we can get rid of those. Alpha is 1.2 over 0.9, which is 4/3 of a radian. So now we can work out what this bit of the height is. We know that this is 0.9, and we know that this little extra bit of height is going to be 0.9 cosine alpha. So that gives us that h prime is 0.9 cosine alpha plus 1. So now we have everything we need to solve this equation for V. Okay, the last question. Now, this again is, so this is a projection question, and they've given us, very nicely given us an equation there for position of y in terms of x. They're asking us to find the two values of k. So this is obviously a quadratic equation, so we're not surprised there's two possible values. Now, the first step is to plug in the 2 points which we know are on this parabola or this curve. So let's plug in a is equal to 14k minus 0.8 1 plus k squared, and that 2a is 42k minus 7.2 1 plus k squared. And so we have two equations. We can get rid of the a and solve for k. So this gives us that k is either equal to 2 or k is equal to 1/2. So that's simple, just solving quadratic equation. In fact, you can even factorize. It doesn't require use of the formula. So now they're asking us about the larger of the 2 possible angles. Because how do we know which value of k is associated with the larger larger angle. Well, what is the angle of projection? This is not, this is a curve, it's not a straight line, so it doesn't have the same angle at all times. Of course, that angle changes. But let's consider a curve. And at some point, we draw the tangent line. You may be familiar with this. We make that into a nice triangle, and then we consider this as the delta x and delta y, change in x versus change in y. And this as some angle. Let's call this theta. And you can observe that the tan of theta is equal to delta y over delta x. Now, if I make this triangle much, much smaller, the usual sort of deriving calculus way, as these things go to 0 length, tan of theta is dy dx. And remember that this is a theta that's only valid at a given point. It's not valid for the whole curve. This expression is in general valid for the whole curve, but you always have to specify, if you want a number, you have to specify which point you're evaluating it at. Now, we are evaluating it at the very beginning. That is our angle of projection. It's what it was projected at time equals 0. So the tan of our theta, let's call it theta naught, is equal to dy dx evaluated at x is equal to 0. Now, what is that? Well, we're given an expression for y. So we've got that dy dx. This first term just becomes k, subtracting some constants times x, because this x squared becomes 2x. And then if we evaluate that at x is equal to 0, this x is 0, this whole thing disappears, this is equal to k. So we have that the tan of theta is equal to k. Now, the tangent function is just one which at least at first increases. In fact, it always increases with increasing theta. So we know that a larger value of k corresponds to a larger value of theta, rather than a smaller one. All of that to establish that the k that we need to be looking at is the k is equal to 2 equation. And in this case, you can just see from what's gone before, tan of theta is equal to 2. Use your calculator. Theta is equal to 63.435, as they say. Now they're asking for us for the time. So we can just use the equation that distance traveled is equal to velocity times time. And therefore, the time is equal to the distance traveled over the x component of the velocity, I should actually mention, because this is a vector equation. So there's two independent components. So here it's 14 over 35 cosine theta, which is 0.894 seconds. Last piece. They want us to find the speed and direction, the motion, when it passes through B. So first we need to find A, which is part of the coordinates of B. So with our value of k that we chose, the equation now becomes y is equal to 2x minus 1 on 49 x squared. And if we plug in the values from the point A in, we find that A is equal to 24. So if we plug in A or B, and this gives us that the y coordinate of B is equal to 48. So we can just use conservation of energy here again. It's not, remember, it's not asking about time. So unless it's asking about time, try and avoid using kinematics, all those constant acceleration equations. Go straight for conservation of energy. So speed and direction of motion. Well, conservation of energy at this point, the energy has 1/2 mv squared. at the beginning point, 1/2 mv naught squared is equal to mg hb, which is, or yb, plus 1/2 mv prime squared, where this is the new speed that we want. We know v naught, we know the mass. In fact, the mass all cancels, never mind that. We know v naught, we know g, we know hb, we can get v prime. No problem. And they also want the angle. So remember that tan of theta evaluated at some x is equal to dy dx evaluated at that same x. And here that x, that point is b. So the angle at that very point moves that. So this is equal to 2. So we go back to our equation here. 2 times the x coordinate, which remember is 2. So dy dx is just 2 minus 2 over 49x, and x here is 42, and that's equal to the tan of theta, and that will give you an accurate result of 15.95 degrees. And that's the end of the paper.